Good afternoon. My name is Burkan, and I'm a professor in the School of Civil and Construction Engineering at Oregon State University. My co-authors are Dr. Deborah Glasser, who is currently an assistant professor at the University of Western Washington, and Professor Jason White from Oregon State University. In this talk, I will present our work on the development of a non-equilibrium thermodynamic modeling framework for ordinary Portland cement and supplementary cementitious material systems. First, we would like to express our sincere thanks to the AC Awards Committee for recognizing us for this humbling honor. And we think that it's a good opportunity to reflect on Alfie Wason, to whom this award is dedicated. He was the president of AC almost a century ago, and he was an exceptional materials researcher. The ship that you see on the screen is the SS Leonard Wason, which is a lightweight concrete ship produced for the US military and was given his name to honor his contributions to our understanding of concrete materials. The paper that's shown here is about using concrete for fabric mills, and it's definitely a very interesting read that we highly recommend. Mathematical models have been an integral part in cement and concrete sciences for over a century. We can go all the way back to 1896 when Ferret mathematically defined the strength of concrete in terms of volumes of air, water, and cement. In 1947, Powers and Browner systematically developed a model for pore volumes and pore structure, which we still use today. It's impossible to list all of these works here, but it's important to note and acknowledge the progress that has been made by many researchers over the years. The prediction of the results of chemical reactions using thermodynamic principle is not a new subject. There are several software tools that can be used to study geophysical problems in cement science. Among the available tools, we use the GAMS platform, which is based on the Gibbs free energy minimization algorithm. Thanks to the amazing work of Dr. Barbara Lautenbach from EMPA, Dr. Dimitri Kulik from Paul Scherrer Institute in Switzerland, and their teams, we have seen substantial advancements in cement and concrete research as a result of the use of the GAMS platform. We built our study on these foundational works to predict the reactions of cement and SCMs. But first, let's start with a simple case without SCMs. Assume that we want to know the reaction products when we mix a particular ordinary Portland cement of known composition with water. We can, of course, explore this problem experimentally, but the question is, can we make these predictions using thermodynamic calculations? In fact, we have had this ability for a relatively long time. If we start with a simplified version of the problem, in other words, reaction of cement with water at equilibrium, which can be considered at infinite time, the way we do this is as follows. We first calculate the amount of each clinker phase, halite, belite, aluminate, and ferrite, alkali oxides, and any other phase that exists in OPC, and provide these amounts along with the amount of mixed water to the thermodynamic modeling algorithm, which calculates the formed solid phases, such as calcium silicate hydrate, calcium hydroxide, AFT and AFM phases, and any other phase that might form, as well as the pore solution composition. We will also have information about the pore space. But we think that it's important to understand how this algorithm works. Therefore, I'm going to go over the Gibbs free energy minimization algorithm through an example, very simple example. Assume that you have 1 kilogram of ordinary Portland cement, and you're mixing that with 400 grams of water. You know the composition of ordinary Portland cement in terms of its clinker composition, with alkali composition, the amount of gypsum it had, and many other compounds it may consist. And you provide this input data to the GAMS free energy minimization algorithm to find what kind of products we form. Now, we know that when ordinary Portland cement and water react, we would get calcium silicate hydrates, calcium hydroxide, AFM phases, AFT phases, and the pore solution will also have several ions with different compositions. The question is, can we use the Gibbs free energy minimization algorithm to predict how much of these individual compounds form? And the answer is yes. The principle of Gibbs free energy minimization algorithm is relatively simple. Basically, let's see if we assume that if the compounds that form, the phases that form, the pore solution composition that forms after the reactions are these values, we can actually calculate the Gibbs free energy of the system when we know the thermodynamic properties of all these materials. And let's say that calculated Gibbs free energy is this point. Now, if we guess another set of quantities for each of these phases and for solution chemistry, we actually could get theoretically a smaller Gibbs free energy, and we know that from the laws of thermodynamics, the smaller free energy is going to be the favored system. So this output 2 will be more favored over the output for 1 that I showed you before. And we can keep doing these successive iterations, calculations, to find the lowest Gibbs free energy state of the system. And the solution to the problem, which is basically what compounds would form and in what quantities, will be the state at which the Gibbs free energy is minimized. So successive iterations of these calculations will give us this lowest Gibbs free energy state, for which we can assume that these compounds and pore solution composition will provide the stable equilibrium system. There is an interesting question here. Does this algorithm work even if we don't know what the output products might be? So if you don't know that you're going to form CSH or calcium hydroxide or AFM or AFT phases, will you be able to guess their formation? And the answer is yes, as long as the Gibbs free energy minimization algorithm is coupled with a thermodynamic database that contains all or most possible products of cementitious reactions. Such a database exists. You see a snapshot of the SemData database here. The SemData database, which is maintained at ENPA, allows the successive calculations of all possible combinations of cementitious products that might form in a system, and determines the combination of the phases that will minimize the Gibbs free energy. This means that if a reaction product is not in the database, the algorithm cannot predict the formation of that product. Therefore, it's crucial to maintain these databases and update their data regularly for better predictions. So far, we have been talking about the prediction of reaction products of a neat OPC system at equilibrium or infinite time. Can we make these predictions at any time, t, or at a given degree of hydration? In fact, we have had this ability for a long time thanks to the seminal work of Parrott and Killer, who developed a kinetic model for the 4 clinker phases, A light, B light, aluminate, and ferrite. The Parrott and Killer model, or the PK model, can provide how much of each of the clinker phases will be available to react with water at any given time or at any given degree of hydration. Using this information, we can provide the thermodynamic model only the amounts of clinker phases that are available to react with water and accurately predict the time-dependent reaction products. The figure on the right illustrates such an analysis. You see the degree of hydration in the horizontal axis and the volume fraction of input and output phase on the vertical axis. You will see that over time the clinker phases will be consumed while the hydration products will form. This discussion brings us to our contribution. Our work extends the non-equilibrium, in other words, time-dependent thermodynamic modeling approach to systems containing SCMs. In this work, we incorporate unique aspects of SCMs that make the prediction of reaction rates highly complex. So what do we want to do? We want to predict, using thermodynamic modeling, the reaction products of a known amount of OPC with known compositions and known amounts of SCMs with also known compositions. However, this process is not trivial. One complicating factor is the Pozzolanic reactivity of the SCMs, which is a key parameter that tells how much of the SCM is available to react. Also, The PK model is specifically developed for the OPC clinker phases and does not cover SCM oxides. Our work fills these gaps in the literature. First, we developed a Pozzolanic reactivity test to determine the maximum degree of reactivity of any SCM. Second, we extended the Pareto and Killoy model to cover main oxide phase of a typical SCM. On the right, you see the modified Pareto and Killoy model, or the MPK model, that covers the clinker phases and SCM oxides. We will not go into details of the MPK model as it is highly mathematical, but more information can be found in our papers. However, I would like to talk briefly about the Pozzolanic reactivity test. This test is intended to simulate the Pozzolanic reactions of an SCM with calcium hydroxide in the presence of a simulated pore solution. We allow these reactions to take place and we measure two properties, the calcium hydroxide consumed and the amount of released heat. By plotting these quantities on a figure with known reactivities, we can quantify the maximum reactivity of the SCM. For example, in this figure, the asterisk, the star, the blue star, indicates an SCM with about 80% reactivity, while the triangle here indicates an SCM with 60% reactivity. The key feature of this test is that it provides a numerical value for the degree of reactivity of the SCM, so that we can use it to determine how much of each of these SCM oxides will be available to react. With the new modeling framework, including the Pozzolanic reactivity test and the MPK model, we can perform non-equilibrium thermodynamic modeling of systems containing SCMs. The figure on the right shows the volume fractions of input and output phases of such a simulation as a function of increasing degree of reaction. The benefits of this approach become clear when we compare the predictions with experimental data. Here you see the comparison of an OPC and silica film system with respect to calcium hydroxide content, pH of the pore solution, and pore solution resistivity. As you can see, when the developed framework is used, the predictions are very close to the experimental data. However, the predictions that do not consider the kinetics of the SCM reactions as shown with the blue triangles in the first and the third plot, the SCM reactions fail to provide good comparison. Similar experimental comparisons can be made with systems containing fly ash. In this slide, we actually show comparisons of OPC fly ash systems with respect to calcium hydroxide content, pH of the pore solution, and sodium ion content. As you can see, the developed framework using the MPK model can predict the experimental data pretty accurately, but those that do not consider the MPK model and the reactivity of the SCM cannot provide good comparison. As I get closer to the end of my presentation, I would like to show you a couple of applications of how we use this modeling framework. One of the key applications of the modeling framework I showed you has a very practical outcome. In our recent work, driven by our PhD student Keshav Bharadwaj, we upscaled the pace level predictions of the thermodynamic model to concrete. This upscaling process allows us to predict key performance properties of concrete, such as concrete strength, resistivity, formation factor, and porosity. These all play important roles in service life prediction models. Here, on the right, we show some example predictions and their experimental comparisons for porosity and formation factor. Another practical outcome of the developed modeling framework is the ability to thermodynamically calculate chloride binding isotherms. As you can see in these figures, the chloride binding isotherms of OPC and SCM systems can be determined using thermodynamic modeling principles without the need of carrying out very time-consuming experimental studies. Finally, I would like to emphasize that we can use the thermodynamic modeling framework in a Monte Carlo-based simulation algorithm to run thousands or even millions of simulations to understand material variability. In this approach, we generate the compositions and reactivities of cementitious materials from statistical variability of the materials. We also present the results from a statistical point of view. This tool has allowed us to study material variability within a geographical region or even within an SCM production plant. I would like to thank you for your attention. I'll be more than happy to answer your questions.